Hello students, welcome to the physics session. So now we will be discussing vertical circular motion and few more concepts from work energy power. Yes, be in line, circular motion and few points related to the collisions as well. So first, vertical circular motion. To understand this, you have to recollect back the concept of horizontal circular motion. Horizontal circular motion. So let me give you briefly here a few points about horizontal circular motion. We have discussed the uniform circular motion in a plane chapter, right? That circular motion is also called as horizontal circular motion. Means in a plane, horizontal plane, if in a horizontal plane, if a body is undergoing circular motion, we call it as horizontal circular motion. If it is the center of the circle and if r is the radius, and if a particle of mass m is revolving in circular path, then the force here you can say that in uniform circular motion, we also call it as horizontal circular motion, the speed will be constant throughout the path. Throughout here the direction of velocity is given by the tangent drawn at that point, gives the direction of velocity at this point. This gives velocity, the tangent gives velocity direction at every point, velocity direction, and magnitude of this velocity is called speed. Speed will be constant here everywhere. Speed is equal to constant, whether here you can mark the points with the different names p, q, r, s, any points. Everywhere speed will be constant in uniform circular motion or horizontal circular motion. Horizontal circular motion. So for example, if you take one string, attach a small bob at one end of the string and hold the other end of the string with your hand and whirl it in a horizontal circular path, then velocity, so that you try to maintain uniform speed. Okay, provided here this is the string with the mass m. If the string with the mass m, when it is rotating in horizontal circular path, the tension will develop here. The tension in the string will be same everywhere, same everywhere. And of course here the bob will have some mass, so mg will act downwards, tension will act in this direction. So the difference between these two will give you centripetal force. Centripetal force, so tension will be same everywhere. So and hence you can also say, of course this may be here when you are in a horizontal circular motion. Actually, if you consider this is D. You have to be careful about this mg, guys. Mg will be acting vertically downwards, but this will be horizontal circular motion. This will not play any role here in mg. So you can say tension will provide centripetal force in horizontal circular motion. It will be constant throughout. Tension will be constant throughout. But it is not like in vertical circular motion. Velocity here throughout, the speed will be constant. Here in vertical circular motion, it is not like that. And even tension will be constant throughout, but here it is not like that. So if you remember these points related to uniform circular motion or horizontal circular motion, then you can follow the actual part of your vertical circular motion. Let us consider vertical circular motion. Means a particle or a body is undergoing circular motion in vertical plane. Say in front of you there is a wall, the classroom wall. That wall is called vertical plane. On top of your head the floor is there, right? You can consider the ceiling or the floor you can consider as the horizontal plane. But the in front of you guys there is a wall, a screen or wall is there, right? That can be considered as a what do you call vertical plane. In that vertical plane, if a body is moving, in that vertical plane, if a body is moving, then in that vertical plane, let me draw you here little bigger one. This is a vertical plane. Even in a, if you just exactly if you look in front of you, the wall, that will be the vertical plane. And that vertical plane here, somewhere here, if you consider a string is there, it is fixed to a some needle kind of, and you have attached a bob of mass m here, and it is this string is free to rotate here. So if you just pull aside and release it, it may undergo oscillatory motion. It may undergo oscillatory motion, but we are not trying to make this to undergo oscillatory motion, but but you are making this to undergo vertical circular motion. You just pull aside or you throw just so that, so with some particular with a particular velocity, so that it is undergoing vertical circular motion. It goes up, it goes to the top, and again it comes here, and again it undergoes like the circular motion. In this path we have to consider, keep in mind a few points. So just like in the above case, here also, here actually in vertical circular motion, mg acts vertically downwards, tension acts in this direction. Let us mark this is point A, bottommost point we call it as. This is center, this is bottommost point is A, and this is topmost point, let us call this as B. Topmost point is B. Okay, this is, let us consider this point is C and this point as D. Okay, now if you throw this with some velocity at this point, with some velocity, let us say v1, okay, or v at va also can take, whatever it is, any symbol you can take. If you give a minimum velocity so that it has to complete vertical circular motion, what is that velocity you have to find? Okay, to understand that, let us bring at any point here, we call this as arbitrary point, at an angle. If you pull this aside for an angle theta, the bob is here, mg will act downwards. By symmetry, this will be theta and this will be mg cos theta. This you have to follow, guys, carefully, then only you can understand. Then this will be, this component will be mg sin theta. Here tension T will be here. T at this angle, you can take it as a T at in terms of angle. At this angle, here it will be different. At A, you can call it as TA, and here it will be different, here it will be different, here it will be different. Tension will be different at different positions in vertical circular motion. Now, by applying law of conservation of energy, you can say from law of conservation of energy, you can say the total energy at A, the total energy at A is equal to total energy at, let us consider this point is some arbitrary point P. So total energy at P, at some arbitrary point P. So we can say total energy here, if you want, you already have discussed that total energy is nothing but potential energy plus kinetic energy. So potential energy at this point, if you take this as a reference line, potential energy plus potential energy at A plus kinetic energy at A is equal to potential energy at P plus kinetic energy at P. When you bring this aside through some angle theta, let us say with respect to this line, it has raised through some height h. This has raised through some height h. So because of that, it may possess some potential energy. At A, if you take this as reference line and height is 0, potential energy at A is 0. And when you give some initial velocity v1 to this object at this point, then kinetic energy can be taken as half m v1 square is equal to potential energy here is nothing but gravitational potential energy mgh plus kinetic energy here as the velocity at this point. If we take it as vp, it is actually a function of theta, so half m into velocity at this point. You can take it in terms of the angle, you can take it as v at a point p, vp you can take, or v at an angle theta in terms of angle. Now here from this, on simplifying, you can say m gets cancelled. On simplifying, you can say v theta is equal to, if you cross multiply here, becomes 2gh. So plus v theta by 2 to cancel, then you can say it is equal to v1 square minus 2gh under root. This is the velocity at any point. in terms of velocity at this point and height. This also can be represented in other terms. That is, specifically, if this string is having a length L, and if this L acts as a radius of circle, and then you can write this L as it is making a string is making angle theta. If you resolve, we'll get L cos theta here and L sin theta here. So from here to here will be L, and this will be L cos theta. This term will be L cos theta, and from here to here total length is L. In this L, if you subtract L cos theta, you will get H. So from the figure, we can say H is equal to L minus L cos theta, or this is equal to L into 1 minus cos theta. So L into H is equal to this. If you replace here, you can write in terms of theta. But V1 also you can write in a different form. So that to understand, you have to understand one more point about the tension. So here this we can also write it as V at any angle theta is equal to square root of V at lowest point or bottommost point square minus 2G H is L into 1 minus cos theta. Right? This formula you have to remember, guys. Now let me give you one more condition here. In terms of tension. So tension. The tension at the bottommost point acts in upward direction away from the point of contact of the body. Here also away from the point of contact of the body. Here also away from the point of contact of the body. Tension acts in this direction always, away from point of contact. This is point of contact. So away means towards the center. And in this case, here mg acts downwards, tension acts upwards. Here mg downwards, tension in this direction. Here mg and T both are in the same direction. And here mg is in the downward direction, tension will be in this direction. Now, if you observe the bottommost point and topmost point, if for the string to just to cross this topmost point, it should have at least 0. It shouldn't have a tension 0 or less than that. It should have more than 0 tension. That means it should have minimum value of tension. Then only it can cross this position. So, or you can say that here the difference between these two gives you centripetal force. Here the sum of these two, T and mg, will give you centripetal force. So at the topmost point, you can say at topmost point B, you can say that tension should not be less than or equal to 0. Or you can say that centripetal force usually is the sum of these two is centripetal force. T plus mg is equal to centripetal force, that is mv square by r. Velocity at that point you can take it as some v2 or v at b, and then we can take it here v2 or v at b. So we want to find the minimum velocity of the body to cross that point, so that circular motion is taking place. So as tension can be 0, or it shouldn't be less than but equal to 0 or more than that. So if you take tension at this point is 0 at point B, topmost point, for the vertical circular motion to be taken place, tension should be greater than or equal to 0. That is the condition of tension. If you substitute this condition, we can write this as m v2 square by r is equal to mg. If m gets cancelled, then we will get the minimum velocity v2 should be equal to square root of gr, if r is the radius. Here if you have taken r is the radius, but if that radius, if you take it as L is the radius, then you can take this as gl, square root of gl will be the minimum velocity at the topmost point for vertical circular motion to be completed. Write down this. This formula you have to note down this, guys, and while doing the numericals, direct numericals also may come up, so you have to remember this. What is this? Minimum velocity at topmost point for vertical circular motion to take place. Minimum velocity at topmost point should be to take the vertical circular motion to take place is v2 is equal to square root of gl. Okay, very good. Next, we'll try to understand what should be the minimum velocity. This is minimum velocity at topmost point. Next, what should be the minimum velocity which you have to give? Minimum velocity when you are just pulling this or where you are throwing, so that it has to undergo vertical circular motion. How much velocity you have to give to this so that it undergoes vertical circular motion to complete this vertical circle? Otherwise, it will go somewhere here and falls down. What is disconnected? Net is disconnected.
Not net, sir.
One
Whole
second.
vertical is discovered.
Okay. Just a second, guys. I'll get. Hello, students. Sorry for the disturbance. There is a small network issue in the system. Right. Okay. Let me give you quickly the briefing of a few points related to this vertical circular motion part. So the minimum velocity at the topmost point for vertical circular motion to take place is root GL. V2 equal to root GL or VB equal to root GL. Okay. Whereas the minimum velocity, or you can say the critical velocity at the bottommost point. You can say minimum velocity at bottommost point, minimum velocity at the bottommost point, minimum velocity at bottommost point for vertical circular motion to take place, or vertical circular motion to take place means for one revolution to take place, for vertical circular motion to take place is, yeah, just again you have to apply what you call the law of conservation of energy only, but between what you call the bottom point and the topmost point, everywhere the total energy has to be constant. So you can say the total energy at bottommost point A should be equal to total energy at topmost point B. That means potential energy at A plus, you can write it as a PE, potential energy PE, or you can use the symbol U also. Potential energy at A plus kinetic energy at A should be equal to potential energy at B plus kinetic energy at B. Okay. So by making use of this, we can say potential energy at A is 0 because reference level is 0. Kinetic energy at A is half m v1 square, or you can take it as va square. This is what you're supposed to find out. Is equal to potential energy at b. So as b is, again you can write here this circular vertical circle with center o, and this is one diameter, this is another diameter, this is point a, this is point b. The top bottommost point, it is topmost point. If its radius is r, so the height, this is reference level. From here to here, what is the height when it is raised to this? This is radius from here, this is radius. So r plus r, 2r will be the height. So you can say this is mgh. H is nothing but 2r. Plus kinetic energy here, you can take it as this is the velocity, this is velocity v1 here, this is velocity v2. For the vertical circular motion to take place, the minimum velocity at b should be equal to kinetic energy is half m v2 square, but because v2 for vertical circular motion to take place is nothing but square root of gl. So v2 square is just gl. So by substituting all here, if you observe m is constant and in common, you can take it out. Then you can write v1 square is equal to 2 into 2 becomes 4, 4gr, 4gr. This r can be, if this is a pendulum of length l you can take it as what? R is equal to l. So 4gl you can take, 4gl plus, if this 2 comes here, it becomes 2 by 2 is 1. So plus v2 square, v2 square is root gl square is gl. So that is v1 square. So 4gl plus gl is 5gl. v1 square equal to, so therefore v1 is equal to square root of 5gl. This is the minimum velocity has to be given to the a particle or a body to complete vertical circular motion. The minimum velocity given at the bottommost point to complete vertical circular motion is this. The minimum velocity to be possessed at the topmost point to complete vertical circular motion should be root gl. But minimum velocity given at the bottommost point to complete vertical circular motion should be root 5gl. These conditions you have to remember. Next, at any point, at any arbitrary point like this, what should be the velocity? Already have discussed this, right? At any arbitrary point, velocity is nothing but what is that? V at theta is equal to v1 square minus 2gl into 1 minus cos theta, right? If you substitute those values, v1 square is root 5gl, v1 is root 5gl, v1 square is 5gl. So 5gl minus, if you expand this, it will be 2gl minus half minus plus 2gl. So it gives you 5gl minus 2gl is 3gl. So you can write this as, from that you can write it as equation 1. This is equation 1, and this is equation 2. Okay, and this is equation 3, let us say. From 1 implies the critical velocity at any point. Critical velocity is nothing but minimum velocity required uh, at that point for the circular motion to be complete. That is the meaning of it. Critical velocity. Critical velocity. Critical velocity at any point. At any point. Critical velocity at any point on vertical circular motion. On vertical circle is, from equation 1 you can say v at any angle theta is equal to square root of that v1 square minus 2gl into 1 minus cos theta, right? Here v1 is this, so if you substitute this, you will get is equal to square root of v1 square. v1 is the square means root will go off, 5gl minus, if you multiply this, you will get minus 2gl minus half minus plus 2gl cos theta under root. So 5gl minus 2gl is 3gl. So v at any angle theta is equal to square root of 3gl plus 2gl cos theta. Or if you take gl out, what you can write? This you can also write it as v theta is equal to square root of gl into 3 plus 2 cos theta. Either way you can write. Both are correct only. This you have to remember. Critical velocity possessed by a particle or a body in vertical circular motion is square root of 3gl plus 2gl cos theta, or gl into 3 plus 2 cos theta. Yes. Now you can take at any arbitrary position. Theta equal to 0, bottommost point. Theta is 0 means cos 0 is 1. So 3 plus 2 5 root 5 gl at bottommost point. At topmost point theta will be 180, cos 180 is minus 1, so 3 minus 2 1, so root gl at like in circular path. Okay, at the bottommost point you have to take it as theta is 0. At the topmost point, theta should be 180. At this point, you can take it as this is A, B, C. Means theta here should be 90. Cos 90 is 0. You get root 3gl. Here the velocity to be possessed for the vertical circular motion to be completed should be root 3gl. So difference between these two velocities should be root 5gl minus root 3gl is accordingly can take, okay, by applying what you call it conservation of energy only. So we can also follow few other related points. This is about the velocity at critical velocity of a body to be possessed to complete vertical circular motion. Minimum velocity at the bottommost point, minimum velocity at the bottommost point, minimum velocity at the topmost point. These 2 points are important out of all, and this is also important. This is arbitrary point at any arbitrary point, critical velocity at any arbitrary point, at any point. Whereas tension, minimum tension in the string, already while getting the velocity at the topmost point, we have considered one condition. The tension should be greater than or equal to 0 condition we have taken. Likewise, tension at any arbitrary point if you want. So we can say a minimum tension. Minimum tension. Next point. Minimum tension. Minimum tension in the string. In the string. Minimum tension in the string uh, to just complete vertical circular motion. To just complete vertical circular motion. What should be the minimum tension? Again, to understand this, I have to consider that arbitrary point, like the point over here. I have considered, right, like this kind of point, like that kind of arbitrary point only I have to consider. Let's draw this diagram once again to understand. This is vertical circle. This is center O. This is the string with the block B. This is the diameter, and this is okay, of course, another diameter. Let's consider the arbitrary point. This point is arbitrary point, point P. This is string with the length L, and here you will have. I consider this is mg. If you pull this string through an angle theta, so that if this is mg, by symmetry this will be mg, this will be theta, so this will be mg cos theta, and this here and this direction tension will be, so here mg sin theta will be there, mg sin theta will be there. But so as we want to find the tension at any angle theta, we have to understand that centripetal force is nothing but at any arbitrary point, centripetal force is this minus this gives you centripetal force. So we can say tension at this angle theta can be taken as T, actually T minus mg cos theta equal to ma square by r. Here therefore T at theta is equal to ma square by r plus mg cos theta. M at that point you can take it as m v theta square at that particular angle, or vp square or v theta square, any representation you can use. Mv at that theta square by r is nothing but L here, plus mg cos theta. But v theta, we already have got the expression for v theta. This is v theta. So v theta square means without root you will get. If you substitute that and simplify, then you will get this is equal to m by L into v theta square is what is that? V theta square gl into 3 plus 2 cos theta, or 3gl plus 2gl cos theta. 3gl plus 2gl cos theta is v theta square plus mg cos theta. Now this is what? T at any angle theta. Now if you multiply with this, what you will get? So m by L, L gets cancelled, you will get 3mg plus here also L gets cancelled, 2lg cos theta, right? So 3mg plus 2mg cos theta plus mg cos theta plus becomes 3mg cos theta. So we'll get 3mg plus 3mg cos theta is the tension at any arbitrary point. Or you can take mg out and you can write mg into 3mg into 1 plus cos theta also can mention. Right? You can also write this as 3mg into 1 plus cos theta. This is the what tension at any arbitrary point. So at this point, if you want theta equal to 0, cos 0 is 1. So 2 into 3, 6 mg will be the tension here. At topmost point, theta is 180, cos 180 is minus 1. Tension will be 0. 1 minus 1 is 0. At this point, 90, cos 90 is 0. So 3 mg will be the tension. So like this you can write you can find the expressions for tension at different positions also. At bottommost point A, at topmost point B, or at C, or at D. At C and D you can say both are same because they are in the same horizontal level. So these are briefly few important points about vertical circular motion guys. Okay. Here, uh, if you go little deeply, few special cases also we need to concentrate. Okay, but this brief idea I'm giving you. Next, I would like to add few points to collisions. Let us discuss briefly now. Already we have discussed the collisions in 1D. What are the collisions and what are different types of collisions, and what are one-dimensional elastic collision and how to find final velocities after collision, and we have worked out some examples also based on that. Now we will discuss briefly about coefficient of restitution, coefficient of restitution, and how to work out few points related to coefficient of restitution. And ballistic pendulum, we'll see briefly about ballistic pendulum also. Let us see now collisions part. Collisions, already I have discussed this in the class. Now this time continuing this part only. Coefficient of restitution and related part, and also ballistic pendulum under this. Or let me give you first what is ballistic pendulum, then coefficient of restitution part. Ballistic pendulum. Ballistic pendulum. What is this ballistic pendulum? Simple pendulum. Simple pendulum is a string, one and a half. This is attached to a bob, a string of length L attached to a bob of mass M. It is if you pull this aside and leave, it undergoes oscillations. So it is called simple pendulum. Ballistic pendulum is also similar to this, but it will have a fixed rigid support and a string. To the other end of the string, a big wooden block will be attached. Okay. Now, if a bullet is fired, a bullet of mass small m is fired with some initial velocity u, it will come and embedded in it. It will come and embedded in it. So, and these two, if this block is having mass capital M and this is having mass small m, these two together will raise us to height, some height h, some height h. So let us say this height is h. So together, m small what is that? Bullet and block together. That means a small m plus capital M together will raise us to this height. So that means both will moves with a common velocity. Let us say v. Actually, here if we consider initially when bullet is coming, this block is at rest. So its initial velocity is u and this initial velocity is 0. After this bullet strikes this, both will embed it and both will move with common velocity. If you remember one definition called perfectly inelastic collision, now we can understand that this is an example for perfectly inelastic collision. Perfectly inelastic collision. Just a second, guys. Right. See, if you apply the law of conservation of momentum for this, then actually ballistic pendulum is used to find the velocity of bullet. Velocity of bullet. It is actually, you can say this is an arrangement or a device also we can call. An arrangement arrangement used to measure velocity of a bullet. Okay, is to find or measure velocity of bullet. Here the bullet fired is called ballistic pendulum. Is called ballistic pendulum. Okay. Now by using law of conservation of momentum, we can say the initial momentum of the total system of two bodies is equal to final momentum. Initial momentum is nothing but you can say we can say that from here from law of conservation of momentum. Here, if you discuss all this step by step, then it will take more time. Just a direct relation note you can take. Okay, from law of conservation of momentum, you can say that m1 u1 plus m2 v2 is equal to m1 v1 plus m2 v2. Here m1 u1 is m small m u and it is what at rest, so plus 0 is equal to after collision it will embedded and small m plus capital M together will move the common velocity. So here if you want to find the velocity of the bullet, you should know what is this. So here what we will say, in different ways we will try to understand this. From this you can calculate what is common velocity. V is equal to mu by m plus capital M. This is if you by knowing the initial velocity of the bullet you can find out the common velocity after collision. If you want to find the velocity of the bullet, okay, velocity of the bullet, here we have to use law of conservation of energy. Law of conservation of From law of conservation of energy, you have to say that uh, as uh, total, I can say just after once it strikes this bullet strikes this, at that moment the total energy of this system is equal to total energy of the system at this point. You can take this as point A and this is point B. Total energy of the system at point A is equal to total energy of the system after raising to this height. In this way you can say this total energy is kinetic energy, and if you take this as reference level, height will be 0, potential energy is 0. So total energy at A is equal to total energy at B. Total energy is kinetic energy, that is equal to half into total mass is m plus m into it is moving with common velocity v. So v square is equal to the total energy is potential energy plus kinetic energy. It will stop here. So kinetic energy is 0. Potential energy will be mgh. M is small m plus capital M into g into h into h. So here m plus m is common. If you cancel this, then you will get this v is equal to square root of 2gh. V is equal to this and V is also equal to this. Okay. So if you equate these two and if you know the height, in terms of height and masses, you can find the velocity of the bullet. So from 1 and 2 you can say 1 and 2 implies 2g. V is 2 h equal to this. Got it? Or you can say u is equal small u is equal to m plus m into v by small m. So you can say u is equal to v is u. I can express this as small u is equal to m plus small m. Okay. Yeah, into v by m. So it is equal to m plus m by m into v is square root of 2gh. This, by knowing the masses and the height raised, we can find the velocity of the bullet with which it is fired. On this height, you can also express it as, if it is a pendulum is having a string of length L, this is L and this is H, then you can say this is if it is raised to height means it is raised to some angle theta. Then you can take this H as if this is L, this will be L cos theta, L sin theta. L minus this is L, this is actually L, and this part will be L cos theta. L minus L cos theta is H. H is equal to here also L into 1 minus cos theta. So if you substitute this here, you can instead of taking this in terms of angle, you can take. So u is also equal to m plus m by m into square root of 2g into 2gl into 1 minus cos theta. In terms of this also, you can express this velocity of the bullet. Okay, this is called what you call ballistic pendulum, and it is the one of the use of this. One of the use of this. Under this collisions only can use by using the concept of collisions you can use this. So whereas what is coefficient of restitution? Coefficient of restitution. Coefficient of restitution. Coefficient of restitution is denoted by the symbol E. E, and it is defined as this ratio between, you can write down this guys, you have to write this everyone as a formula. It is a ratio between relative velocity of coefficient of restitution, write down everyone, coefficient of restitution is equal to relative velocity of separation after collision. Okay, relative velocity of separation after collision, it is ratio between this and relative velocity of approach before collision is called coefficient of restitution. You can put this in a box. It's very important formula. Mathematically, if you want to find out, in case of especially elastic collision, so if you have bodies m1 moving with initial velocity u1 and m2 moving with velocity u2, initial velocities before collision. After collision, m1 is moving with velocity v1 and m2 is moving with velocity v2. So here, if u1 greater than u2, then only collision will take place. So if it is moving faster than it hits it, then it will may move faster and it may be moving a little slow. So for the collision to take place, this should approach this. So relative velocity of approach can be taken as, in vector form also can take. Okay, u1 minus u2, u1 minus u2, relative velocity of separation will be v2 minus v1. So you can take this in mathematical form as relative velocity of separation will be v2 minus v1. In vector form, if you want, you can write v2 vector minus v1 vector also. The relative velocity of approach is u1 minus u2. u1 will be greater than u2. So u1 vector minus u2 vector also can take. This is a mathematical way of representing coefficient of restitution. Here, try to note down few points, related points. This coefficient of restitution, note, E is equal to, number 1, E is equal to 1 for perfectly elastic collision. Means for perfectly elastic collision, relative velocity of approach should be equal to relative velocity of separation. If these two are equal, they will cancel and they will get 1. That is the meaning of it. E is equal to 1, comma, for perfectly elastic collision, that is, you can say u1 minus u2 is equal to v2 minus v1. Okay, whereas E is equal to 0, E equal to 0 for perfectly inelastic collision or completely inelastic collision. For perfectly inelastic collision. Okay, and for any other collision like semi-inelastic or semi-elastic collisions, like kind of collisions, E value will varies between 0 and 1. So for semi-elastic collision, E will be varying between 0 less than E less than 1. For you can say this is for perfectly inelastic collision. So if you say inelastic, that is nothing but semi-inelastic. You can also call it as semi-elastic. Perfectly elastic, semi-elastic, or semi-inelastic. Semi-inelastic, semi-inelastic, or simply you can also call it as inelastic. You can also call this as inelastic. For all these kinds of collisions, E value will vary between 0 and 1. It is equal to 0 for 0 for perfectly elastic collision. Sorry, 1 for perfectly elastic collision, 0 for perfectly inelastic collision. You may get direct questions, concept-based questions based on these points also. For perfectly elastic collision, coefficient of restitution is, options will get E equal to, for perfectly elastic collision, E equal to 0, E equal to 1, or 0 less than E less than 1, or E greater than 10 or greater than 1. Some options will be given. So for perfectly elastic collision, E should be equal to 1. That's it. Equal to 0 for perfectly inelastic collision. You have to remember this part. Okay, right. These are briefly about some of the points related to collisions, one-dimensional collision, perfectly elastic one-dimensional collision already I have discussed, and in general, and this is the example. What you call ballistic pendulum is an example for perfectly inelastic collision, and coefficient of restitution will be considered for different collisions also. By an application point of view, you may come across a body which is dropping from a height. So if it is perfectly elastic collision, E will be equal to 1. So what is the height raised? This kind of questions you may come across. Let us see briefly one of the example based on that. You can consider it as application or special case or whatever it is. Application, that is, if a small body of mass m is released from rest from height h, and if it while it interacts with the earth, it undergoes perfectly elastic collision. Then after collision, it may raises to height h1. In terms of h, what is h1, you may ask. Or like this kind of questions, some different interrelated questions will come. It may undergo not only one collision that it goes to height, then it comes back and undergoes second collision. Like that, it will bounces n number of times. After nth bounce, what is the height raised? What is the height raised in terms of this initial height? You may ask like this kind of questions also. So first, battery is low, guys. So let me finish this. This is a very important application. Let me finish this. Then I will wind up. In this case, we have to consider just before this body small m strike with the ground. Ground will be taken as a big body called earth. Big body called earth of mass capital M. So initially, when it is approaching towards this, it will be at rest. So its initial velocity here, if we take this as like this, small m is moving some initial velocity, capital M is at rest. So here u1 is u and u2 is 0. But this u is nothing but in terms of actually the maximum velocity obtained by a freely falling body after passing through a height is nothing but this u can be taken as u is equal to square root of 2gh. By we have to remember this freely falling body case, guys, then only can understand these points. Now with this velocity, if it strikes, this is at rest. Earth is a very big body, it will not move. This only will bounces back. It will rebounce. So it means it will come here, it hits it and bounces back. So now the case is, if it comes from this height, to what height it will raise. So while raising with same as it is perfectly elastic, velocity will not change. With same velocity only it will bounces. With what velocity it is striking here, with what same velocity it will rises up. That means 2gh velocity will rises. Then to what maximum height it takes place? It may rises is the question. Let us say this is h1. After raising to this maximum height, its final velocity will become 0. This we have to make use here. So by using this what you call equations of motion, we can say v square as we want the distance. So v square minus u square equal to 2as. V square minus u square is equal to 2as. Here v will be 0. U is 2gh under root. So square will be minus 2gh. But 2a is nothing but minus g here. Okay. But s is h1. So it is 2gh1. So here actually here one thing, guys, actually here just I would like to apply what you call the definition of coefficient of restitution. E is equal to relative velocity of separation by relative velocity of approach, v2 minus v1 by u1 minus u2. So here v2 velocity of the second body, anyway after collision also 0, minus v1 will be this, but in opposite direction. So you can take it as square root of 2gh, okay. And after collision it may have to take it as, of course, root 2gh. And here u1 minus u2 is 0, u1 is u1 is you can take this as mm, yeah, here we can take the velocity. This is the final v2 minus v1, right? So final velocity of this is 0. This final velocity of is initial velocity. Final velocity you have to take this as after collision. The final velocity can be taken as the velocity reached by this after coming back. So it is equal to this height, not this one, because of this collision. This is not equal to root 2gh1 it is, and this will be root 2gh. So we can take it as the square root of 2gh1 by 2gh. 2g cancel, will get square root of h1 by h is e. If you square on both sides, we will get e square is equal to h1 by h. So the height raised after first collision is h1. This is what we are supposed to find. h1 is equal to e square h. E is the height raised after first collision in terms of height. It is fallen from initial height from which it is fallen. Okay, this is what you have to. This is what the relation you have to use. After first bounce, height raised is this. After second bounce into 2, third bounce into 3, like that. If you after nth bounce, you have to write this as a general formula here. After nth bounce or collision, height raised, height raised is hn is equal to e power 2n into h. This as a general relation you have to make use, guys. This is a very important relation. Remember, there are so many other related applications out there. Right now, just you can go through and you can work out few examples based on this. Okay, as the I don't want to just give you with make you to feel more complex with so many of applications. I would like to stop here, so you can go through this and remember these points. At least you can work out few numericals instead of remembering going through so many applications and confusing. At least remember these few basic points. Okay, the classroom, guys, we will be there only. I'm coming there in 2 minutes. The online students, you guys go through this and try to practice all the questions which you have worked out in the class.